Good afternoon and welcome to our third Hydrogen on Materials webinar. And at the start, few practical issues. So duration of this webinar is including a question and answer session is roughly 50 to 60 minutes. And for the question and answers, you can submit your questions, ask a question tab to be shown on you. And then a special issue is that if you are on the full screen mode, you cannot see the tab, so remove from the full screen mode. And after this webinar, we will provide you with webinar slides and recording roughly within a week after this webinar. And here is the agenda for today. So we will have three technical presentations, starting with the large-scale hydrogen storage issues, then heading for hydrogen safety and some application examples. And the third one will be discussing modern materials and how materials modeling enables, let's say, wise material selection for hydrogen services. And then at the start, few words about VTT. So here's a slide showing some basic numbers if you are not familiar with VTT before. So VTT is a visionary international research and technology organization. And we are having some roughly 2,400 people or experts working in different fields in VTT. And we are turning the big challenges for sustainable growth and jobs and well-being for people and environment. And then heading for the hydrogen topics as such. So VTT is partnering with the companies throughout the hydrogen value chain. So starting from the hydrogen production to the storage and transport, and then heading for hydrogen use and conversion. For example, creating e-fuels, e-chemicals from hydrogen and CO2. And one of the hot topics in the future will be the use of bio-CO2. And when thinking about what we are doing in the hydrogen, so of course traditional research on processes, equipment and materials, but then of course techno-economic analysis, calculations, piloting, and a roadmap work, and not forgetting these safety criticality issues. And at the moment we have a quite nice vast hydrogen infrastructure, so from hydrogen production to use and conversion. But in the next year we will have a new facility, so piloting plant for clean energy transition. So that brings us new competencies for the future. And then, as I mentioned, this is our third webinar on hydrogen. And if you are interested, you can still download the previous presentations looking from the net. And we will provide this information also to the slide set, what you will receive after this webinar. So first one and the second one. And then it's time to move the actual technical presentations. And the first one will be given by Pasi Valkokari and talking about large-scale hydrogen storage. So please welcome Pasi.
Thank you, Pekka. Yes, the topic is today on my side, the caverns and shafts for hydrogen storages. And I'm going to approach this topic via presentation of the Hydrogen Underground project. Short name of that project is HUG. My name is Pasi Valkokari and I am a senior scientist representing Industrial Circular Economy team at VTT. So when going to the first assumptions related on what the PF-supported, Business Finland-supported HUG project is about. We started from the assumption that large-scale hydrogen underground storage is a key enabler of the hydrogen economy, especially when the green hydrogen is in question. It allows hydrogen production and consumption to be decoupled from each other, enabling cost-efficient green hydrogen production and providing stable and reliable supply to its users and hydrogen derivative manufacturers. In short words, so when there's no wind nor sun to produce green hydrogen, the demand for the hydrogen product could be still fulfilled when we have industrial scale hydrogen storages. And what the target is? The target is in this project to create a basis for large-scale underground hydrogen storage concept in the business and technology ecosystem of the Finnish hydrogen industry. Building a competitive advantage for international business, that's our target also. That consists of technology and services. And large hydrogen reserves ensure the stable fossil-free renewable energy system and supply of hydrogen to further refiners and seamless ecosystems operations. And of course, when we are thinking about the Nordic soil or land bedrock conditions, that could be a problem for us to establish such an underground hydrogen storage system, since we don't have natural locations like salt caverns for these purposes. And so we have to really understand what is demanded and how it's possible to establish this solution of storage solution to hard bedrock. And the results, there is still mentioning that 1 to 3 technical and economic case studies will be as a result in this project. But nowadays the direction is so that we are going to present 3 technical and economic case studies and make a bedrock studies in one location. That's our aim. And techno-economic assessment, roles of companies in the value chain and business model for storage and distribution are considered. And we will also result in a roadmap together with the ecosystem partners. IP landscape, what is happening in this field of hydrogen economy is one of our topics, as well as the safety issues and guidelines for permit procedures are one main topic in our project. And later on today, you will hear not only from results, safety study results from the HUG, but more wider perspective to the hydrogen safety issues presented by Tero Välisalo. Like I earlier mentioned, the approach in this project is very holistic, to be said. And in the project, we are taking into consideration the requirements from both sides on the green hydrogen value chain members. And of course, when we are talking such technological system as hydrogen storage will be, also from the perspective of that kind of technological system life cycle perspective. Perhaps the end of the life aspects are not that much considered during the project. But in any case, the approach is as wide as possible. And what are our so-called work packages? What they are containing are there is a study of ecosystem and business models, and there has been, in the cases, variation in the targets of different companies. So this is an important thing to understand when constituting such an technological solution. Like earlier mentioned, safety and sustainability, also responsibility issues are highlighted during the project. And perhaps the main area, one of the main areas of this project is design concept and technology studies and research. And this is containing both the crucial site selection methodology and as well as the bedrock investigation methodologies. And in this part, the design concept and technology, also the first calculation of feasibility, economic feasibility of such a solution will be made. We will also take into consideration the life cycle and operation phases and think about proper, for instance, proper operational models, operational procedures, and what could be the proper life cycle definition for such an technological system. And here's our short example considering the use cases that we are having. And at the moment, I must say that they don't differ so much between each other. Mainly differences are in the likely technology decisions, and two of the use cases are covering so-called lined rock cavern solution, and one of the use cases is a lined rock shaft or similar, the smaller kind of solution compared to the original industrial scale target. But then the main difference is coming from the operational, or let's say also the business model side. And in one use case, the aim is still a little bit vague, but in use case 2, the likely business model is a so-called hydrogen as a service model. And in the use case 3, the actor is thinking about how to store hydrogen mainly for own usage purposes. And when you are looking at the scale of these use cases, this is based on the VTT's current view and therefore the scale indication is more or less indicative. And yes, and like the note says that in use case 3, the importance of these previous couple of use cases is therefore important that this actor is also thinking about how to be a hydrogen as a service actor, so to serve multiple users that are demanding green hydrogen. Then we have still approximately 10 months time to deliver Hug babies, so our results. And the project started in the beginning of April last year and will go on until the end of March 2026. So we have also been talking inside a Hug consortium what should be next, what kind of questions should be asked or solved next. And please note, these are the results of the Hug consortium discussions. These are not representing the whole project portfolio of that VTT has in the hydrogen economy side. And we are going to have an application, hopefully left to Business Finland decision making during this summer, that is considering about integrated hydrogen and methanol production kind of issues. So what kind of solutions could be made for production sites to better understand and control the life cycle issues of such production sites. Then there is a short name IRMA, which is concentrating on liner structures and construction methods, and PF Helo, which is focusing on the production logistics and optimization of hydrogen value chain. These are such project preparations that we are willing to invite more partners to come along, and more or less the HELP consortium is already ready. And of course there are room for potential EU projects, and but at least we should have some kind of further answers to after hook research before starting so-called Hug 2, which is aimed to be a pilot project to construct a pilot hydrogen storage. And the contact person or coordinator of these actions you can see on the bottom left corner of this slide. Then one thing I would like to highlight still is the power of many. So we have many actors along, altogether 20 organizations, and which of them two are research organizations, And I, in this highlight the, besides VTT, the role of GTK that has been producing quite a good information considering bedrock studies and so on. And total project volume is a little bit less than 2.6 million euros, and time schedule I just mentioned in the earlier phase of this presentation. So thank you all, and hopefully we receive good questions considering this topic as well as the other topics of this webinar. Thank you.
Thank you, Pasi, for an interesting presentation. And next one will be Tero Välisalo and talking about hydrogen and safety issues. So please, Tero, go ahead.
Thank you, Pekka. My topic is about safety. I'm a research scientist in human factors and system safety team at VTT. Been working for safety issues of hydrogen for about last 5 years, almost full time. So I am telling you about basically 2 topics. I will continue where the same topic Pasi started, which is this underground hydrogen storage thing, and main risks and some Finnish aspects on the safety studies, and also some words about hydrogen safety in maritime applications we've been involved in for many years now. First, I'm not gonna talk about a lot about general hydrogen hazards, but just to remind you that what we are dealing with quite interesting substance here. Combustion hazards are of course the main part. Jet fires and different kinds of explosions like deflagration and detonation, which is the most severe thing if detonation occurs. Then, of course, the gaseous hydrogen is in high pressure. Pressure hazards as such are always considered. Then cryogenic hazards, if we are dealing with liquid hydrogen, which is not the topic today. And of course, the degradation of metals and alloys, which have been dealt with in the previous webinars. So I'm starting with this hydrogen underground topic. The main risk, of course, is leakage, meaning the loss of containment of this cavern, which is basically a huge hydrogen bottle, and the leakages can occur anywhere in the pressurized tank structure, but we assume that if it is in the liner structure, they are at least in the first place they are relatively small, because there is always firm rock structure behind the liner. But the weakest spot is probably the surface connection in the cavern. But if we are talking about the most critical part, it is the surface connection as a pipeline, because in that line there could be a really massive release of hydrogen, which can, of course, lead to an explosion on the surface. So the other type of hydrogen underground storage is this line rock shaft, and of course the same risks apply to this as in LRC, but additionally, because there is not the rock mass over the cavern, we must somehow engineer the plug on the surface so that it will not pop off because of the pressure. And there are some challenges because it cannot be, the plug cannot be very long because it shortens the effective volume of the storage. But it still must tolerate all the dynamic movements. This pressure affects onto the structure. So it is really challenging part to engineer. Some words about underground hydrogen storage permitting in Finland. The main player here from the authority side is Tukes, Finnish Safety and Chemicals Agency, and with them we are also cooperating in doing the HAC project. So what was quite surprising when we talked about this pressure equipment directives and pressure equipment legislation, this kind of quite huge pressurized cavern is not considered as pressure equipment currently. There are some discussions going on, but let's see how they proceed. These processes are normally quite slow, so nothing will happen in the next few years, I guess. So the acceptance of this underground hydrogen storage goes along the normal process of chemical facility that requires safety report. The limit is such low that if there is over 50 tons of hydrogen on site, only hydrogen, if there are other substances, then it is less. Then it goes to the safety report category, and there are lots of different safety studies that must be done, but it is still not a pressure equipment as such. Consequence analysis are one vital part of this permitting process, and there are some scenarios that must be dealt with consequence analysis methodology. The leakage scenarios for the pipelines with the largest cross-sectional area and pipeline with the highest pressure, and I guess in underground hydrogen storage this is the same pipe. The surface connection will be the largest with the highest pressure, because I guess in many cases the pressure will be reduced after the storage right away. And the leakage rate must be calculated for leakages of 10% of the cross-sectional area of the pipe. So if there's pipeline with 100 square centimeters, so we have to model the leakage for 10 square centimeters of that pipe. So that's the idea. But we don't have to consider risks like uplift failure or plug failure, because those should be dealt with rock engineering design, system design. So this is something that shouldn't be modeled as such, nor the kind of tank explosion. If the underground hydrogen storage is a tank and there is a flammable mixture in it and it ignites, we don't have to deal with that. There must be such technical features that prevent that from happening. Consequence analysis consists of basically two things: heat radiation analysis. There are 3 different heat radiation values that should be checked, and what must be notified here is that the amount of hydrogen does not really affect the results. If there is a jet fire and volume of hydrogen, the jet fire is the biggest jet fire flame will be in the very beginning of the leakage situation. And another is this pressure effects of an explosion. There are also some values that should be checked, and it is recommended that there is no over 10 kilopascals pressures outside the property, this facility property boundaries. And also here, the amount of hydrogen does not really affect the result here. Then the other topic, maritime sector. There are lots of things going on maritime, and they just published this net zero regulations for global shipping this spring, and hydrogen is one alternative to reach these goals. Both gaseous and liquid hydrogen has been applied to ships, and there are new built ships and retrofit ships where diesel engines are replaced with fuel cells and electrical drivetrain. So, and there are no applicable rules specified for hydrogen yet. I think lots of things are happening here. Safety challenges are mainly in high pressure system. The storages are usually built in sea containers, and they are placed on open deck, and there are lots of high pressure cylinders in the containers, either in vertical or horizontal position. And this means that there are quite a lot of fittings and lots of potential leakage sources. And because of the hydrogen properties, it is really hard to detect if there is a small jet fire, especially on open deck. And there is always danger for potential escalation of fire if the fire damages the composite cylinders, which are basically plastic, which cannot tolerate that long jet fires. There are leakage detection possibilities, of course, hydrogen sensors, but they are not that applicable in open deck conditions. Infrared cameras for flames, and also acoustic sensors, which are detecting the sound of leakage. And the most critical hazard for the hydrogen storage on board is fire. And one problem is if there are pressure relief valves in the system, they will not necessarily work properly in composite cylinders, because the composite material is kind of an insulator. The pressure does not raise inside the cylinder that much, and that therefore there are these TPRDs, thermal pressure relief devices, in the system that open automatically in case of temperature raises above set limit. And those valves are also used normally in hydrogen cars, but in hydrogen cars the amount of hydrogen is around 5 kilos or so, and here the amount of hydrogen is more, several hundreds of kilos. So it takes time to empty the system, and if we are thinking about the situation where there is fire on board, why should the released hydrogen ignite? It will ignite, I guess so. Is it safe to release hydrogen in an emergency? That's a question. And there are also manual emergency release options. Then just a couple of pictures, final pictures here. We have this kind of hydrogen-powered ships already. One example is H2 Barge 2 operating in Netherlands in Rhine River, and the home harbor is in Rotterdam, and they are using gaseous hydrogen swappable containers, so on. The owner is future-proof shipping in Netherlands, and this is one of the partners of the flagships project where VTT has been the coordinator since 2019 when the project started. The other one, also flagships result, is Zulu 6, which is operating in Paris area, Seine River, and it's a bit smaller vessel, also operated with gaseous hydrogen, compressed hydrogen, 300 kilos on board. There are also batteries as a backup. And the final slide about Hydra. This is the one. This is not a part of Hydra, this flagship project, but it is an operational vessel in Norway, and they are using liquid hydrogen. Actually, in this picture, I don't see the tank, but it should be just next to the wheelhouse. But anyway, just an example that hydrogen is already in maritime sector and expanding, I guess. Thank you.
Thank you, Tero. And I hope that audience will have a good questions for Tero about the hydrogen safety issues. And then the third presentation of today will be given by Tomi Suhonen and talks about material modeling and how material modeling should help on material issues in hydrogen. So please.
Thank you, Pekka. Hello everyone, my name is Tomi Suhonen. I'm a principal scientist and a manager of VTT ProperTune, which is VTT's concept of integrated computational materials engineering. So VTT ProperTune, it's an ICME concept. It has been developed over the last 2 decades. It started first small with a group of people, maybe a handful. It was quite academic, but during these 20 years, it has been grown quite a lot. So VTT ProperTune is now operated by 60 researchers doing only the computational materials engineering. And then at VTT, we do have supporting teams doing the experimental part, which is done. The models, they do need experiments. We need inputs from characterization. And of course, experimental validation of the model is always nice, so we can trust the predictive capability of our approach. The idea over here is that this allows us to create microstructurally accurate materials and their operational loadings in realistic conditions. Everything digital and virtual. It has been used to optimize a wide variety of material properties and product performances, such as wear, corrosion resistance, fracture, fatigue durability, and other lifetime metrics. VTT ProperTune, it provides a systematic requirement-based design approach. It also provides a digital framework for material discovery, design, and optimization. It decreases component costs due to the improved design process, and it enables improved and disrupted discovery of novel designs and material solutions, leading to improved products. One of the carrying ideas is that the ICME approach, it reduces the time to market of new material solutions quite a lot. So faster R&D than with the traditional trial and error approach. So what do we model? We model quite a lot of things. It's not a single program. We utilize all kinds of different scales, whether it's a size scale or time scale, different modeling techniques, different libraries for different purposes. Typically, when developing a material, we know that dependent on the chemical composition and how you manufacture it, whether it's casting or you process it somehow, the processing dictates the microstructure fully. The microstructure, again, dictates all the properties that the material has. And of course, the properties, they fully determines your performance of your material solution over there. So basically, you can look at different steps or go, for example, from a performance requirement and back engineer it to properties, to structure, to process, and so forth. Even though the computational capabilities has improved in recent years, still some of these physics-based methods are computationally quite time-consuming. So now artificial intelligence and machine learning has been speeding up those things. So maybe not as accurate as fully physics-based models, but they can give us nice direction where to look with a little bit more detailed techniques. In many cases, we start from the performance requirement. You want certain lifetime for your component or system or material and go from there. Okay, some use cases. So like I mentioned, even though we started from a quite academic background, VTT ProperTune has been developed together with our industrial partners and applied to their materials and products. This has gained pretty good acceptance in industry quite widely. Couple of examples. If we start from the ArcelorMittal case, ArcelorMittal is world's largest steel manufacturer. They contacted us that could we computationally develop a better performing steel? They told us that you cannot change the composition, meaning that don't add any expensive alloying elements over there, but you can change the thermomechanical treatment, which is done anyway for these type of martensitic steels. We said that, okay, let's pick some application area. They sent us their best performing steels. We characterized those steels. We created the microstructural models. We combined that microstructural model to the application models and started to change certain hierarchies and sub-hierarchies in the microstructure systematically. We went through thousands of different material solutions computationally. We proposed 4 different solutions to them. They believed us and actually manufactured those steels in a large-scale steel mill. They tested those, and the outcome was that the new steels that we designed, the performance improved from 200 to 250%, which was pretty good result. And nowadays you can buy that steel from the store. So that's a good thing. Other example over here is Caterpillar. Due to the legislative problems with coating solutions like hard chromium, they were looking for alternatives. They had found pretty good candidate to do that, but they asked us whether it could be still better. We looked at that and optimized the processing computationally, and the outcome was 40% improvement in certain metrics. And one example from Finland, so we have worked quite a lot with Wärtsilä, dealing with different engine components operated with different fuels and so forth. And over there, they say that the design accuracy improvement is 3 to 5-fold, and they are able to capture product failures much, much easier, or possible product failures. One example of the techniques that we use, this is an example of metal additive manufacturing, meaning 3D printing. This could be any manufacturing technique, but we can go basically computationally throughout the whole thing. So we can design the alloy with the smaller scale methods like DFT, MD, Monte Carlo methods, so forth. We can model the laser material interaction over here, how it melts, what vaporizes and how much, and so forth. So it's a multi-physical and multi-scale modeling of the powder bed physics. We can compute the solidification structure, phase field modeling, and Kalfat methods over there. We can look how the alloying elements segregate and what type of microstructure we will get. We can look at part, process, and system design. So in this case, the scanning strategy, how it should be done. So it's a part scale thermomechanics and microstructures. When the part has been printed, we can start to look at the properties. We have the scale-dependent and dislocation dynamic-based crystal plasticity models, where we can look at the properties, and also performance models. So look at, for example, how hydrogen exposure is affecting the performance, how the microstructure, defects, inclusions, surface roughnesses affect in fatigue or creep or different performance metrics. So VTT ProperTune, it's a toolset, it's a collection of software libraries and tools for solving multi-scale materials and multi-physical modeling problems. It enables efficiently and rapidly set up novel modeling workflows and solvers to address materials modeling and simulation challenges. The multi-scale over here, meaning size scales, for example, from atomistic to microstructures into the component scale. And these are coupled directly with multiphysics. So whether it's hydrogen embrittlement or other topics, you can look at those. We deal with all kinds of different materials, metallic materials and alloys, thin films and composites, different coating solutions, different ceramics, whether it's oxides, carbides, nitrides, different manufacturing techniques, whether it's casting or additive manufacturing or what else, but also with plastics and composites, polymeric biomaterials, and bioengineering materials like proteins and so forth. So it's a quite wide variety of materials that we can deal with. Then, if we look at this quite simple concept, how to construct the hydrogen interaction with materials, we know that hydrogen as a small element penetrates materials quite easily, so we need to have a model for the hydrogen uptake. Whether it's liquid hydrogen, gaseous hydrogen, or so, it needs to be coupled into atomistic modeling toolset to see how the hydrogen penetrates the material and where does it go. And this atomistic small scale is then coupled into the microstructural model. So polycrystalline model, most of the engineering materials are like this. So at the center we have the hydrogen transport model, which is connected to this continuum, little bit larger scale model of hydrogen effects on plasticity. Hydrogen can also change or induce phase changes in materials, similarly as we know from steels how carbon affects whether it's austenite or ferrite when you adjust the amount. Hydrogen does the same for materials, and then of course also this hydrogen-aware fracture model, because that's typically a concern for material users in a hydrogen-containing environment. And these are then coupled into the more component scale macroscopic hydrogen sensitive model over here. Okay, a couple of equations. Let's not go too deep into this. But when talking about mechanical performance of components and so forth, we approach those with these crystal plasticity models. So over here you have this colorful picture showing the polycrystalline material. The different colors means that the orientation of that grain is certain and they are different. And why this is important to take into account and not to treat this as just a one box is that all the different colors and crystal orientations has different properties. So if we load this cube, the certain stress hotspots will appear as in red over here and cold spots over here dependent on the microstructure. So if this is not taking into account, then the predictive capability and the link to realism is quite small. We have different slip systems in BCC lattice, we have 24, and FCC we have 12. But besides this, we need to, when talking about hydrogen, we need to take that into account as well. So there is certain equations how to deal with. Is there a hardening, is there a softening, or what is happening over there? Besides this, we need a diffusion model. We need to take a look how the hydrogen is going inside the grains, what happens when you have dislocations in your grains, and also look at the grain boundaries over here. So the hydrogen immersion energy, which is shown over here at the y-axis, and hydrogen transport direction at the x-axis, is that it requires more energy to penetrate the actual grain. Through dislocations, it doesn't require that much energy, and the lowest energy needed is at the grain boundary. And this is also the reason why we talk a lot about hydrogen embrittlement. Here's one example of calculation of hydrogen concentration going through polycrystalline steel. So the hot spots means that there's a lot of hydrogen, and blue spots over here that there's basically none. After that, we can start to play around with different parameters and compute how different materials, how different microstructures, if it's manufactured this way, is it cold rolled, what has been done to that. And for the validation, we see exactly the same as we see in the models when we compare to the failure analysis cases from a real world. So hydrogen is a problematic material, but this can be captured by these computational efforts. Besides this modeling part, we do have quite nice material testing in infrastructure at VTT. We can look at the hydrogen embrittlement cases. Also at high temperature, we can expose materials and test pieces to hydrogen. We do have facility for hydrogen tribology. So if we talk about some moving parts, for example, look at wear or frictional topics. We do have analytics for hydrogen diffusion, solubility, and trapping. And of course, we do have quite state-of-the-art characterization possibilities in terms of microscopes. So state-of-the-art SCMs, TEMs, equipped with all kinds of different detectors, focused ion beams, so forth. And now the latest new thing related to hydrogen is we just installed a new time-of-flight SIMS. This is really nice because it can detect hydrogen, unlike SCMs and TEMs, because of the hydrogen is so light element. But also the experimental part is quite nicely covered, and we work with different industries going from marine to industrial applications into storage, transport, and infrastructure. But thank you. That was my presentation today.
Thank you, Tommy, for a nice presentation about modeling. So some of the slides, pretty heavy stuff, including a lot of equations, sorry, but it's a promising approach. But now it's time to move the question and answer session. So please provide the questions to the Ask Question tab, which you can see after going away from the full screen mode. So actually at the moment we have received a couple of questions already from the chat side. And then the first actually to Pasi, you were talking about this large-scale hydrogen storage. So how you see, one big storage or multiple small ones?
Well, actually, the conceptual work is going on at the moment, and hopefully my answer doesn't differ from this viewpoint that I have now. I'm keen on to produce a somehow modularized solution where there are several tanks considering hydrogen storaging at the almost same site, because I see it also risky thing that we have one big tank for all that, which can be down based on one failure. And if we have several tanks, perhaps smaller ones, but still several tanks, we have some kind of redundancy considering that.
Okay. So, and then directly to Tero. So, Pasi was talking about the tank sizes and modular or so, but how you see from the safety perspective?
One big or a lot of small. Well, it depends on the situation. If the system is totally isolated from bigger network, if there's a hydrogen network or like nationwide, it is possible to get rid of the hydrogen via the pipelines. But if the system is isolated and there's no connections to anywhere and there occurs a leakage, I don't think in case of large hydrogen storage it is possible to just release it like in hydrogen cars or maybe in hydrogen ships. It is not feasible. The substance is expensive and there's lots of risks if you create a huge hydrogen cloud on site, and the release will last quite a long time. So if there are several storages, there should be some room for the kind of pumping or transferring the hydrogen from the failed storage to another, just to keep it there. Because I think the hydrogen is the most safest is to keep hydrogen inside the tank. No, not really.
Yeah. Okay. Yeah. Thanks, Tero. So a short continuation also, let's say more targeted question and going for a actual design. So I guess that this will be discussed in more detail in the HAC project, but how this, let's say, connecting pipeline should be made. Is it in the top of the cavern or a vessel or bottom or somewhere? So what are the benefits and pros and cons in different approaches?
We haven't discussed that much about it, but of course, if it's in the bottom of the cavern, there will not be that much movements in the rock as in the top solution, and even the rock is very solid in Finland. There will be some movements due to the pressure changes. So maybe bottom, but not
so,
yet clear.
So I guess that we will return to this even inside the HAC to some level.
Yeah. definitely.
Okay. And then one detailed question to Pasi. What are the design pressures in the caverns at the moment? Planned. You showed these 3 different use cases.
3 different use cases, between 200 and 500 bars.
Okay, thanks. Then let's see what we have here more.
But of course, it's fluctuation. It's not steady, the pressure.
Yeah. Okay, let's see. It's a little bit lag on the tab at the moment, but when waiting to reply, so a question to modeling and Tommy shortly. So what do you see, or how do you see, what's the biggest challenge in modeling of the hydrogen effects of materials?
Yeah, I think the problem or the challenge is how to validate the models.
Okay.
So related more on that side, because we know that hydrogen is really mobile and it can penetrate, but it can also come out of the material quite easily. So when we are characterizing the hydrogen contents and so forth, we must understand what we are doing.
Yeah, and I guess that there is also differences between different materials and microstructures.
Yeah, absolutely.
How easily the hydrogen moves.
Yes.
Okay.
Yes.
And then you showed this one slide about the hydrogen and material infrastructure. It was quite nice looking, but how do you see this collaboration between different partners and companies, universities?
Yeah, I think it's really beneficial because there's so many different aspects like we saw today related to hydrogen. There's so many different actors and so forth. So typically in collaboration, everyone benefits.
Okay, thanks. Okay, I'm just now looking the clock. We have already run out of time, so we have 2 minutes over time. So if we are getting more questions, we will answer to those questions later on. And so the final slide for this is that you will pretty soon receive a feedback questionnaire. So about your comments, feelings about this webinar. So please provide us impact and how we should improve this, or are there any, let's say, topics that you are really interested for the future. And then you can always contact our presenters. The contact information was shown to you in the after the presentations, and the presentation will be delivered to you within a week. Or then you can contact, of course, us and later. And so one contact is Mika Malkamäki, our solution sale lead on hydrogen issues and material issues. But at this point, thanks to all for coming and listening our webinar. I hope that this has been a informative and good information for you. And if you have any questions for the future, so please contact us and we'll continue. Thanks and bye.